Okay, this is from section 2.7. It's about standard deviation, and so deviation and z-scores. This is my second time running through this video, and so you're going to see me do reveals instead of actual writing. Sorry about that. I felt bad reprinting it again after my second time. So, we're going to talk about computing measures of dispersion, including the standard deviation for quantitative data. And we're going to look at z-scores. What are they? How are we thinking about them? How do we interpret them? Okay. My first remark is really about quantitative data. So quantitative data, I want us to remember that we compute means and medians and modes for those. So when we're given quantitative data, which by the way is numerical measures as responses to our research question, we compute the average. So we compute the mean, the median, and the mode, which are all measures of center or averages. Okay, my second remark is about this word. So quantitative means numerical measurements, and dispersion to me means how spread out. You know, if I think about people dispersing, I think about them running away in all different directions. If I think about water dispersing, it is getting, it's spilling and spreading. And then when I think about something like molasses and how quickly it disperses, I'm like, oh, well, it takes a long time. So here we're talking about our data. And how spread out is our data? Okay, and then one very quick and easy measurement for dispersion is range. Okay, so if we want to see how spread out is the data, the quickest thing to do is take the biggest minus the smallest and find the difference. How much is it between the lowest to the highest? That is one easy measurement for the dispersion. Okay, so, and it's called the range. All right, example 1 is actually a repeat from the section on box plots, which is an optional section, but it's a little bit different. So there are 20 students in a class, all of them scored a 70, which by the way is a sure sign of cheating. Draw a bar graph of this data, find the mean, the median, and the range. Now I'm going to reference back to the old set of notes for box plots because I just wanted you to see this data set. 20 students all scored the same thing, which is a 70. So immediately it's really easy to see that the average was a 70 and that the middle number is a 70. So I wanted you to see that first. And really it's not a bar graph, it's a histogram. So let's show that. Okay, so as a histogram, along the horizontal I put the score, and a score of 70. I didn't even put a scale like 10, 20, 30, 40, blah, blah, blah. Just put a 70, and along the vertical I put number of students, and it went up to 20. So here's my histogram, and for a score of 70, it was 20 of them. And the range, so it says the mean and the median, so the averages were both 70, as we saw. But the range, so between the lowest and the highest, there was no point difference between the lowest and the highest because everybody scored a 70. So this is very telling about how spread out the data is. Well, there was no difference between the high and the low. Okay, in number 2, there are 20 students. Again, half of them score a 50 and the other half score a 90. So I'm going to show you that data set all written out. Half of them, so 10 of them scored a 50 and failed, and the other half of them scored a 90 and got an A. Now the middle number is a 70 because it's halfway between 50 and 90, and the average the mean average, well, there was 50 added 10 times, plus 90 added 10 times, and that had a class average, mean average of 70 as well. So the mean and the median were both 70, but here's where things get a little bit different. The range here, the difference between the highest and the lowest was a point spread of 40 points. That's a lot. That is a really big difference between the high score and the low score, is a 40-point difference. And I went ahead and along the horizontal for my histogram, I put the scores and I went 10, 20, 30, 40, 50, 60, 70, 80, 90. And I stopped at 90 because that was the highest I needed to go. And then along the vertical, I put number of students. And I tried to make 20 about the same height as in number 1, and then 10 is halfway up. So at 50, half of them, so 10 of them scored a 50 and 10 of them scored a 90. Now let's look at this third class. 10 of the students scored a 70, 5 scored a 65, and 5 of them earned a 75. Okay, so written out as a complete data set, 5 of them got middle D's, 10 of them got exactly a low C, and 5 of them got a middle C. Now the middle number is a 70, and if we add up all of these and divide by how many students, which is 20, we also get a mean average of 70. So on average, they also scored a 70. So now let's take a look at some of this other business, right? For instance, the range from the high to the low was only a difference in 10 points. So the highest, between the highest and the lowest scores in the class, there's only a 10-point difference. That says something. That says that they're not spread out. They're all around the middle. And, I mean, they're all around passing, basically. Now for my bar, or I'm sorry, not my, I know I wrote bar graph here, but it's really a histogram. Let's see, on my horizontal axis, I went 10, 20, 30, 40, 50, 60, 70, 80, 90. And you see right at the 70 marker, I have 10 students. At 65, 5 of them, and at 75, 5 of them. So we see that they're all bundled right around each other, pretty close together visually, and we see that this range was 10. 10 points from the lowest to the highest, not too bad between those two. So it also makes a difference when we are reading these things. When we're just given a number, we really do need to think about where this came from, like this range. A range of 40 points from the low to the high, or a difference of 10 points from the low to the high, and how much that really impacts the actual classroom. Like if I came back to the class and handed these back, man, that day would be awkward. Half of them would be depressed, angry, ashamed, and then the other half would be like so joyful that they probably would turn red and blush. So, and then they would feel upset because they'd be like, oh, I'm so sorry that you failed, but I did so awesome. And it would just be an awkward day. But if everybody scored around here, it would not be an awkward day. Everyone would be like, oh yeah, I pretty much got that too. So number 4 asks, which class would you have preferred to be in and why? And ultimately, I asked that question because if you only knew the average, the class averages, you wouldn't be able to tell. But if you see the range, then it will tell you something. Like, if there is no difference between the low and the high, that tells you everyone passed. If there's a little bit of difference between the low and the high, then, you know, everyone is pretty much together. If there's a big difference between the high and the low, then be careful. The question is, where do you land? Yeah? So which class would you prefer to be in and why? a lot of my competitive students say, I'm that one because I'm probably going to win. I'm going to be the 90%, even though they just have a 50-50 shot of passing or failing. The people who like this one are what I like to call my inclusive students. They're like, everybody passes here, but then there's no difference between good and bad, or better or worse performance. And then here, a lot of people are like, well, that's pretty good. That's like safe, where most people are going to pass, and I can differentiate between doing better or worse than somebody else. So, but all of that comes down to the range and the picture, as opposed to just the mean and the median. So now let's talk about the standard deviation. The standard deviation is a measure of spread that computes the average distance away from the mean. And now, I actually have a couple of remarks, even though I only put one bullet point here. My first remark, I left this so that I could put down the formula so that you could see this. So I'm going to actually jot that down quick. So S, for standard deviation, people use S if it's a sample, and they use a lowercase Greek sigma if it is the population. Well, similar to the distance formula, okay, it looks a little bit like this. Okay, and I'm not going to write this. Okay, there we go. And this is all divided by n. So if you ignore the square root and the squares, then you have a bunch of numbers added up and divided by how many you have. So that's the average part of this. And if you ignore the n and this dot, 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 then really this value plus this value divided by half and take the square root, or I'm sorry, not by a half, don't divide it at all. You take the square root and you have found the distance between 2 points. So this is really an average distance between points. But you have a lot of data points, and they're finding the distance to the mean. So that's what we have here for the standard deviation. But I'm going to jot down this other remark that I think is more relevant, and that is the lower the standard deviation, the less distance they are from the mean. So lower standard deviation means closer to average. Mean average, by the way. And a higher standard deviation means more spread out. Higher standard deviation means more spread. Okay, that I feel like is the more important remark. So let's look at these exams again. It says use a calculator or Excel to find the standard deviation for each class. Okay, luckily I have done this. Okay, we're going to go stat, and we're going to select edit, so hit enter on edit. And over here, I have entered 20 70s for the first class, 10 50s and 10 90s for the second class into list 2, and 5 65s, 10 70s, and 5 65, 10 70s, and 5 75s into list 3. And I'm going to go stat for statistics. I'm going to hit over for calculate, and I want the one variable statistics for list 1. That is the first class. So what we see is this is the class average. We see that the sigma, or the standard deviation of our variable, is 0. It also is going to give us, right, if we scroll down, the minimum, the maximum, so we could have computed the range and the median and whatnot. But nonetheless, I'm really interested in the fact that it said that the standard deviation is 0. So 20 students, all of them scored a 70. That means that the standard deviation was 0. They did not deviate. There was 0 deviation in the scores. Got it. Okay, the distance to the average distance to the mean was 70 because the distance to the mean was 0. So the second class, okay, so now I'm going to go back to stat, calc, one variable statistics, but now instead of list 1, which was class 1, I'm going to go here to second number 2 to put in list 2. So second L2, and then there was no frequency distribution, it was just a list, and so I'm going to calculate. And now the standard deviation is 20. So for the second class, the average distance, let's take a peek at that. So looking back over here, 50s, 90s, the average was a 70. The average distance to the mean is 20 points away. Voila, there you have it, you know, there you have it. So on average, how far away was your score, or how far away was your score from the average? Oh, you know, like 20 points. Okay, so the deviation, how far did they deviate from the average is really what's happening. There are 20 students. Oh, here we go. That's class number 3. So let's go back to the calculator, and I'm going to hit statistics. I'm going to go over to calculate. I'm going to compute this one variable statistics, or one classroom's scores of stats. But now I'm not L2, I'm L3. So second L3. So list number 3 was not a frequency chart, so I'm going to hit enter and leave that blank. Ooh. So the standard deviation here, so the class average was still 70, and the standard deviation was about 3.5-ish. Let's write that down. Okay, so the standard deviation here was about 3.5. And if we look back, here's what we see. So 10 of them scored exactly average. 5 of them scored 5 points below average. 5 of them scored 5 points above average. And so the average distance to the mean is 3.5, because these are all zeros. Yeah? So zeros, how many? So like, so this is computing something that is very similar to, you know, the average distance away from the mean, about 3.5. So, oopsie, my bad. Rank these classes in order of their deviation. Describe how the measure of standard deviation can be used to compare data sets. Well, here's the thing. So I would say, first of all, not asked for, is that the average of each one of them were 70. So they all had the same class average, except here, if we rank these, we would go class 1, no deviation from the class average. Class 2, oopsie, I'm sorry, class 3 had the next to lowest deviation, low deviation from the class average. 65s are not too far away from 70, and 75 is also not too far from 70. And then, ordering them by deviation, class number 2, high deviation. Yeah, those scores were a lot different than the class average. 50 is a lot different than a 70, and a 90 is a lot different than a 70. So how would we use these to compare the data sets? Whoa. These are all the same. No deviation means consistent across the board. Low deviation means pretty consistent, but not exactly the same. And high deviation means, boy, they were really spread out. They really deviated away from the class average, and they were super spread out. Now, we're going to go ahead and do example 3, and then I'll stop to make another video for the other. So let's look at these since we're talking about deviation and consistency. Here are some golfers. When you're golfing, the lower the score, the better. And every round is actually 18 holes. So these people played a lot of holes of golf, okay? 6 days of 18 holes of golf. So Brittany scored 75 on 18 holes, 80, 72, 81, 75, and 77. And Jimin scored a 69, 77, 71, 75, 80, and 83. Okay, so in terms of winning, Jimin won round 1, 2, 3, and 4, but lost round 5 and 6 to Brittany. Let's find the average for each player. Probably could have found overall too who won, but now since I'm using the calculator, I'm going to actually do that quick. So going back to my calculator, and I hit stats. I go to edit, and I have entered Brittany's scores into L4, and I have entered Jimin's score into list 5. So now I'm going to go to stat, over to calculate, hit enter on one variable statistics, but now I'm going to go second 4 for L4 and ask it to compute these statistics. All right, so it says mean average. Brittany's mean average for these 6 rounds of golf, about 76.7. I don't know if you can see that, but I just rounded it to 76.7. And Jimin, her average, so I'm going to go stat, calc, one variable statistics, L5, and I did the same thing. For hers, I got 75.8. So on average, she scores about a 75.8. Find the range. Okay. The range is the maximum minus the minimum again. So Brittany, and I'm just going to write it up here. Brittany's range, let's see, the maximum here is 81. The minimum here is a 72. The difference between those is 9. Those are 9 apart. So 81 minus 72. And for Jimin, the range, well, her high was an 83 and her low was a 69. Well, this is interesting. Like, she got tired. 83, ooh, I'm not sure. I'm going to have to check that. That is a difference of 14. Okay, so we found the range, and now the question is, which golfer do you think was the better player in this competition? And which do you think is more consistent? Explain. All right, well, I'm going to compute, well, it looks like I'm going to compute the standard deviation for number 4. So my first question is, maybe just at a glance, which one do you think is more consistent? When I look at these two players, I feel like Brittany is more consistent because her high is lower and her low is higher, so they're closer together. So she's constantly scoring right around here. Whereas Jimin, her low is lower and her high is higher, and so a little less consistent. Now, in terms of who's the better player, I don't know. I don't know that I can say who's better, but I certainly have a measure for this. Okay, so better, I don't know, whoever won probably had the lowest total overall, but more consistent, I would say that Brittany's are all similar in score for each round. Okay, and so are Jimin's, but they're just a little bit less similar. So are a little, oopsie, let's call that little less similar. Okay, find the standard deviation for these two competitors. Does this support your claim? Let's do that. Okay, right. So now I'm going to go back to stat, calculate, one variable statistics. This would be, list 5 was Jimin, standard deviation of 4.8-ish. Okay, so for Jimin, oh, should I go with sample? Do we consider this a sample or a population? I'm gonna go sample style. Okay. The standard deviation, about 5.3. And by the way, that was me deciding that I'm looking at this as a sample, even though it could very well be an entire competition. But anyway, so 5.3, and then I'm going to go stat, calculate, enter for one variable. Oopsie, why did I do that? Second. So calculate and list 4. 3.4-ish. So Brittany's standard deviation was approximately 3.4. Okay, and so here's the thing. Does this support your claim? Yes, actually, because the less this number is, the lower the deviation, the more similar your scores are as a whole. The higher your deviation, the less similar your scores are as a whole. So yes, it certainly does. And I just want to mention, this goes back to the remark right after standard deviation. The lower the standard deviation means the closer the average is to the mean, the closer the data is to the mean. The higher the standard deviation means that the data is more spread out. And so if we think about that with the terminology consistent, if you're more consistent, then you do not deviate as much. Okay? In the next part of these notes, we're going to talk about, what does it mean to be normal? Does that mean you don't deviate? Does that mean you deviate? What does that mean? So we're going to talk about this mathematical idea of normal.